next speaker, Mike Hawkins from Harvard, who will speak on Equivariant, Homotopy, and Localization.
All right, thank you, Jesper. Thank you also for the organizers for putting on this fantastic semester and this conference, and for asking me to speak. Equivariant homotopy theory is a huge subject, and I kind of wanted I think I didn't know that much about it. Over the years, when I was younger, I'd hear kind of grown-up mathematicians talking about equivariant homotopy theory, and they'd be talking ordinary math, and then all of a sudden they'd spell something, and I'd be like, all right, whatever. And so I had this kind of weird knowledge, a lot like what a child has of the adult world, about equivariant homotopy theory. And over the years, I started using it a little more, and then more recently, Mike Hill and Doug Ravenel and I used it in a pretty sophisticated way. And so I sort of just want to share what lessons I learned about learning the subject, about what it's about, and some of the things I think are kind of really fundamental features. So this isn't meant to be historically accurate or complete. Think of it as kind of like fan fiction for equivariant homotopy theory. So first let me just tell you, I just want to tell you, this isn't exhaustive, but just some places kind of to dig in where equivariant, the methods of equivariant algebraic topology kind of really came up, and they're good places to go and read and encounter some of the demands that people made on the subject. So one of the earliest things is in the theory of manifolds. So in the classification of manifolds by surgery, the whole theory works pretty well and easily when the manifolds are simply connected, but in the presence of a fundamental group, things get much trickier. And the game there is to work up on the universal covering space and think of that as a space with an action of a group. So right there, you're trying to study manifolds with group action and make all of the things you're familiar with about manifolds work. And a sort of really early articulation of that kind of problem is something called the space form problem. And there's a nice historical survey of that problem on the Manifold Atlas, which you can find by Googling. So the problem really goes back to the 1800s, but it's stated in what we think of as a more modern term by Hopf in around the 20s. And the question there is which manifolds, or to classify manifolds, have a universal covering, which is have a sphere as the universal covering. So another way of asking that, if we pass to the universal cover, is what kind of groups can act on a sphere? So I have a lot I want to say today, and there's sort of a very elaborate history of this problem. There's a very elaborate answer to it with many, many unexpected turns. And I'll just say this was sort of more or less answered by, I won't give you the answer, but it's more or less answered by E. Madsen, Charles Thomas, and Terry Wall. There's a nice survey of it by Jim Davis and Jim Milgram, which you can also find by Googling. But so I don't want to talk a lot about. This is just advice if you want to learn about how this is used and how equivariant topology is kind of how some of the demands of the subject arise in geometric topology. This is a good question to investigate, and there's a lot of beautiful mathematics here. I'm just going to say at this point, this required things like atom isomorphism in equivariant cohomology. It required some notion of Poincare duality in equivariant cohomology. So however you're going to set it up, you want these two features to be there. Okay, so I'm going to get down to much more concrete things in a minute, but let me just continue with some of the things I found kind of really inspiring to learn about. So another sort of famous problem when I was younger that I remember learning about was something called the equivariant Moore space problem. So this is an interesting question. It comes up like in a first course in algebraic topology. You can make Eilenberg-MacLane spaces, so they have a given group occurring as a homotopy group somewhere, and all the other homotopy groups are zero. And that's something you can do completely functorially in the group. You can make a functor from the category of abelian groups to the category of topological spaces that sends A to Eilenberg-MacLane space KAN. So there's something that sort of you can rigidify in a very strong sense about Eilenberg-MacLane spaces, about homotopy groups. You can ask the same problem, the same question about homology. Can I make a functor from abelian groups to spaces that sends an abelian group to some space whose nth homology group, for some fixed n, is that abelian group and all the other homology groups are zero? So can I realize homology groups functorially? And so this was a question posed by Steenrod, and surprisingly, there the answer is no. You can't realize homology groups functorially, and yet you can realize, well, you can't realize a single homology group only in one degree functorially, whereas you can homotopy groups. So the answer to this is no. And the original answer, so that's the first examples of these were due to Gunnar Carlson. So the answer there is no. And this uses a lot of, this uses a different arena of techniques in equivariant homotopy theory, and it kind of uses an interface of the cohomology of classifying spaces of groups together with the action of the Steenrod algebra. So these are some other things that you kind of need to see entering equivariant algebraic topology. So there's also kind of emerging in the early 60s, around 1960, you can find a lot of this in Borel's seminar on transformation groups. There's a lot of stuff that if I have a space with a G action, what can you say about the fixed point space? So this is a space. This arrow means it has a G action, and this, of course, is the set of all x such that Gx equals x for all G in our group G. What can you say about the fixed point space related to the topology of the original space? And the answer here is that there's a whole arena of theorems that tell you you can see a surprising amount. And so there's a whole series of what are called fixed point formulas. So there's a whole series of fixed point formulas that relate the topological invariance of the space with its G action to the topological invariance of the specific space. And a great place to learn about these is so let me give you an example, and I'll tell you a great place. If you don't know about these formulas, a really great place to start. So a typical example is suppose my group G is a torus. So maybe just the circle or a product of circles. And it's acting on some space X. And X is probably a manifold or a compact CW complex. The action should be relatively nice. So I'm not going to, I'll define more of these things later. I just want you to get a flavor of the kind of results. So instead of cohomology, there's an equivariant cohomology. So X is a space with the group action. And we're imagining for now, I'll make these more precise later, we're imagining for now that there's a that anything we do in algebraic topology we can do in the presence of a group action as well. And so there's the equivariant cohomology of X. And this is a module over the equivariant cohomology of a point, which in this case is, let's suppose I'm using even rational coefficients. It doesn't really matter. But this is, let's say, Q. It's a polynomial ring. So R is the rank of this torus. And the beautiful theorem is that the support, so this is if I think of this in terms of algebraic geometry, this is the ring of functions on an affine space of dimension R, and this is some kind of sheaf over that. And the support of that sheaf is intimately related to the information about the fixed points. And in particular, there's a very beautiful theorem that says if I take the field of rational functions, if I just invert everything, that's isomorphic to this field. Just to save chalk, let me abbreviate this K. That's K tensor the cohomology ring, the ordinary cohomology ring of the fixed points. So this is another theme, and in fact, this often is, when someone says localization in equivariant topology, this is often what they have in mind. You've taken the equivariant cohomology and you've localized it in the spectrum of the cohomology, equivariant cohomology of a point, and then that miraculously turns out to be related to the fixed point. So if you've never encountered this idea before, or even if you have and you've never read this paper before, I highly recommend a paper of Atiyah and Bott called The Moment Map in Equivariant Cohomology. Or moment map, maybe it's called and, I don't remember. Equivariant. So when I was a graduate student, Atiyah and Bott had just proved this, and Atiyah was giving lectures on it. And I definitely had the sense that I went to these lectures, and I definitely had a sense I didn't understand a word. I think because there was a lot of spelling going on, and it was kind of beyond me. But a few years ago, I found the notes I had taken from those lectures, and they were remarkably coherent. We all know that, right? And I could actually read them. But the most striking thing was I had totally forgotten that the title of that series of lectures was called Generalization of a Theorem of Archimedes. So the theorem of Archimedes, I later learned, wasn't just some random theorem of Archimedes. It's the one the one kind of etched in stone on Archimedes' grave. And the theorem is the one, it's the theorem that says if I have a sphere, what most people call a sphere, I accidentally called that a two-sphere in calculus class. So my course evaluations went downhill after that. And then you inscribe it in a cylinder. So here's my cylinder here. And then I just pick any sector. Okay, I look between 2 points here. So on the cylinder, on the sphere, there's some little bent piece of ribbon, and out here on the cylinder, there's an actual, it's what we call a cylinder. It's still a cylinder, it's just shorter, right? And the theorem of Archimedes is that the area of this part of the sphere is the same as the area of that cylinder. So that theorem you can prove with cylindrical coordinates, by if you can remember how to integrate a couple of inverse trig functions. You can also prove it using equivariant cohomology. So if you don't know this, this is to whet your appetite. It's a really beautiful investigation of the fixed, so it's a consequence of this fixed point formula. And that's just to inspire you. Equivariant cohomology comes up in all kinds of crazy places. Can you Google my notes? Sadly, this was before Yeah, before, but the paper's pretty good. Yeah. So, okay. Anyway, that's another place to read about this. There's also a whole bunch of other places, but I think I don't want the time to get away from me. And so there's equivariant K-theory, where the K-theory of a group acting on a space, you study equivariant vector bundles, and this combines the theory of the representation ring with the with topology, and that gives you a way of approaching the representations of compact Lie groups in terms of topology. There was a variation on that Dan Fried and Konstantin Telemann and I did, where you look at the group acting on itself by conjugation, and that gets related to the representations of loop groups. There's a huge number of formulas in representation theory that become clear from this point of view in equivariant K-theory. So all those are sort of many places one might go to learn a little bit more about equivariant algebraic topology. So there's a few things that you I kind of want to sort of unpack and expose you to. So there's a lot of theorems. Well, there's so many more theorems. There's the Siegel conjecture and the Sullivan conjecture, and these sort of open the door to the kind of things Bob was talking about that tell us about the homotopy types of classifying spaces of groups. And there's sort of many aspects to equivariant homotopy theory and the things that they and the things they do for you. So well, okay. So I want to make a philosophical point, and then I'm going to kind of just start into talking about, and really kind of elementary terms, what equivariant homotopy theory is about, how we set it up, and what we do. So, in homotopy theory, we try to do things up to homotopy. We try not to ask for rigid identities. We try to say, well, if two things are going to be equal, we don't want to actually say they're equal. We just want to say, well, they're both points in a single contractible space. We try to free everything up to homotopy theory. And this creates a sort of a philosophical, or a slightly philosophical issue when you're really trying to think about how to set up equivariant homotopy theory. So if I have a space X with a G action and a space Y with a G action, then we want to study the space of equivariant maps from X to Y. Let me just put a G there. So that's, of course, the set of all maps from X to Y, such that f of Gx equals G f of X. So this is fine. This is something we can think about doing up to homotopy. But here I've asked for an explicit solution to an equation. And if I try to relax this, so I'm going to just introduce some made-up notation here at this point. Let me call these infinity maps somehow. So if I try to do the same thing, but I ask that this identity only hold in the infinity sense. So nowadays, infinity, when it's used in algebraic topology, means that somewhere around you're not committing to explicit points or explicit solutions to equations. You just want these to live in a big contractible space of choices. So what I want to say is that this identity isn't asked to hold on the nose. It's just asked to hold up to a contractible space of choices. So this gives you so in equivariant homotopy theory, these two objects are closely related, but they're really quite different. And what we call this, so the catchword for this is something we call Borel equivariant cohomology. And this one's actual equivariant cohomology. Or equivariant, not cohomology, but actual equivariant algebraic topology.
Are you at the bottom just what you'd get if you took the mapping space with no GX and then took the
Yeah, that's right. For some reason, I had decided that I wasn't going to assume the audience knew what homotopy fixed points were. But right. But that's right. It means you, yeah. Or you can say you take a big contractible space with a free G action, and cross X with that space, and look at the equivariant map, the rigid equivariant maps. But I'm not going to. I'm going to focus more on the peculiar features of actual equivariant homotopy theory. So many things in equivariant topology are really theorems about Borel equivariant topology. So this is something that that for the most part you do using the Borel equivariant theory. But these kind of things that go into the space form problem, those use sort of the more rigid equivariant algebraic topology. So one of the things I'm going to kind of just go through the foundations of the subject just from the beginning and tell you some of the peculiar features and tell you how to SPLL a few things. But I just, one of the, as I've gone back through and thought about it in recent years, I found it useful to really distinguish the parts that are kind of Borel and the parts that aren't, and to kind of try to ask myself, how do we say things so that we're doing the infinity version of actual algebraic topology? Well, that was a philosophical remark. It wasn't meant to, it's just going to be kind of a guiding theme. Okay, well let me, so that's enough warm-up and motivation and places you might look, and if you're looking for further references and foundational things, ask me. I'm happy to, I've read a lot of these in recent years, and I'm happy to, when I'm not being recorded, offer my honest opinion about various things. So, okay, so the first thing you have to decide is what kind of groups you're going to look at. And in the space form problem and the things that came up in geometric topology, the groups tended to be the fundamental groups. So they tended to be hopefully finite, certainly discrete, and acting discontinuously on spaces. In the kind of things that were used in equivariant K theory, or in this paper of Atiyah and Bott, you were really looking at a compact Lie group. And one of the things I think that makes it hard when you're just getting into the subject is people got good at setting up the foundations and set it up so that the story worked for both. Well, I guess technically a finite group is a compact Lie group of dimension 0. So it worked at that level of generality. But there are many features that are a lot easier if you just restrict to finite groups. So I'm going to, so for today, I'm just going to consider G will be a finite group. And the first question you have to ask is, we want to do equivariant algebraic topology. What kind of spaces are we going to use? And in ordinary algebraic topology, we use simplicial sets, and we call them spaces, or we use CW complexes. And here, so you start by defining the notion of a GCW complex. And then there's another issue you have to do. You have to decide where the hyphen is going to go here. And what's that? Both hyphens? I guess there's I guess it's not like hyphens. Hyphens are not a. Just took a while for the nickel to drop, but I get it. Okay, you're right, Winnie the Pooh. Okay, so there. Now I have to edit my paper again. And hyphens are, as far as we know, they're not a natural resource, so we can use them as wastefully as we like. Okay, so a GCW complex. So that's like a CW complex, but it's a space built from spaces of the form G mod H cross a disk. Now this isn't this is a decision you have to make right at the beginning. It's not really an obvious one. You might have thought, so H is a subgroup of G. So this is just a collection of disks being permuted by the group G, but the group isn't acting on the points of the disk. And this is a decision, and it might seem like not quite the right thing to do. You might have wanted this to be able to be a disk in a representation of the group. It turns out from experience that this is the better class to work with, and I think it works out that this is the more general class. But anyway, it turns out there were some, after many years of experience, people realized that this is the good notion. Okay, so it's built just like a CW complex from this. And one thing that's going to come up later, I want to give you a proof of something later to really show you how, kind of what I think is really at the heart of the subject. Let me just point out one thing. If I have a space with a trivial G action, like a single disk, and I'm looking for an equivariant map into my space X, that has to land in the fixed point space. And if you think about that, that also tells you that if X is a GCW complex, then the fixed point space is also a CW complex. And X is built from that by attaching cells of the form G mod H across a disk, where H is not all, H is a proper subgroup of G. So this will come up later, but it's something you have to think a little bit about it to sort of, it just follows from this fact that something with no action can't map to something with a non-trivial action in an equivariant way. So I'm going to use this a little bit later, but it's a little basic fact about GCW complexes. Okay, so that's a basic notion. Now, here's one thing I learned by looking in Tom Deek's book on transformation groups. It's another kind of good point about this, that in ordinary algebraic topology, the product of two CW complexes is a CW complex, and the product of a K cell and an N cell is a K plus N cell. But what happens here if I take G mod H cross a disk cross G mod H prime cross another disk? That will be of the form S cross D N plus M, where S is G mod H cross G mod H primed. So if I'm working with a finite group, this is a finite set with a G action, so it's a disjoint union of orbits, and this is just a disjoint union of cells of dimension n plus m. If I'm working with a compact Lie group, then this is a product of homogeneous spaces, and in order to really get the theory going, I have to give this an equivariant cell decomposition, and I'm going to meet cells of higher dimension. So this is the first of many things that fight you. You can solve all these problems, but it fights as it makes the general theory in the compact connected case harder than the finite case. So this is it's just a warning sign. It's easier to learn this by just focusing on the finite group case, and this is already something that happens. Okay, so that's the basic place we're going to do homotopy theory, but we really want to do stable homotopy theory. So let me just write the term. Let me write tau upper G for the space of GCW complexes, or the category of GCW complexes. And let me, in fact, without being very specific, I'll say the homotopy theory of this. So we can imagine this in many ways. We could try to make a Quillen model category, or we can just be naive and think we just want to study this category and equivariant homotopy classes of maps. And the next thing we want to do is stabilize. So we want to do stable homotopy theory. So now here's here's where something really interesting happens. The naive thing to do, would be to just stabilize like we do ordinary algebraic topology. So work with spectra spectrum objects. And in case that's not sort of in your background, what I mean is I want to work in some category where the homotopy classes of maps are calculated as follows. So I want to look at, so let me write this. I'm going to define that to be the limit as n goes to infinity of homotopy classes of maps in that category of maps from the n-fold suspension of x to the n-fold suspension of y. And for this to be a good notion, I think I want to assume at least that x is a finite GCW complex. So this category, I'm not giving it a name because I'm not going to use it for very long. This category is, if you want, a universal stabilization of G spaces. So in the language of model categories, it's the universal arrow to a stable model category or a stable infinity category. So it has the property that cofibrations, so it's additive, maps from a wedge to the product. These are finite wedges to finite products, that maps a homotopy equivalence or a weak equivalence. Cofibrations and fibrations are the same. So cofibration sequences are the same thing as fibration sequences. So it has all those properties, but it's not good enough to it's not good enough to meet the demands that the space form problem was asking about. We don't have Poincare duality. So in this world, you don't have kind of the homotopy theoretic underpinnings for Poincare duality or Spanier-Whitehead duality or any of that. So this isn't quite the right way. This does give you a stable homotopy theory of G spaces, but it's not really the right kind of stable homotopy theory. So this problem, the problem with this is that Spanier-Whitehead duality doesn't work. Okay, so if we think about Spanier-Whitehead duality, what happens? You're supposed to take a finite complex and you're supposed to embed it in a large sphere, and then you look at the complement of the sphere, and the unreduced suspension of the complement and the original thing are duals. Or you have something relating the cohomology of this, the cohomology of the complement, and the cohomology of the sphere. But if a space has a non-trivial G action, it can't embed in a sphere. So if this is really a G space, I'm not going to be able to embed it in a sphere, and I have to embed it in, I can embed it in a sphere that's the one-point compactification of a representation. So V is now a representation of G, and SV is the one-point compactification. So if I want Spanier-Whitehead duality to work, and I go do the exercises in Spanier's book, but I want it to work equivariantly, it's not good enough to take the limit over these over these spheres. I have to actually take the colimit over the representation spheres. So again, I'll write the following notion. I'll write x, y for the limit as v goes to infinity of homotopy classes of maps from SV smash x into SV smash y. I guess, did I use, yeah. So again, so now I'm assuming that X is a finite GCW complex or something. And these are the maps in the homotopy category of some other kind of stabilization, which I'll call G spectra. And this turns out to be the good place to do equivariant stable homotopy theory. So I'm giving you a formula for the value of the maps in the homotopy category in a special case. This category is more sophisticated, but it's rigged so that any computation you want to do can, in principle, be reduced to a computation of this form. Now, this has some good news and some bad news in the sense that it raises a philosophical puzzle. This I could understand if I'm really stepping back and trying to think, well, I'm interested in characterizing this category up to equivalence in the sort of sense that we don't work with objects in categories anymore. We work with categories and functors between them. Then this I sort of have a good algebraic way of thinking about. I'm making a universal stabilization. I'm making the universal functor to some place where cofibration sequences and fibration sequences are the same. But I don't know what I've done here. This is something, it's clear, it's the right place to work. It's the place that the problems that arose that equivariant algebraic topology were supposed to address. It's the right category, but how do I think about characterizing this arrow in terms of categorical data? So I'm not going to give a complete answer to that. I'm just going to use it as kind of a guiding theme today. But some of the things that Mike and Doug and I learned about equivariant homotopy theory as we placed our own demands on the subject started to kind of bring about create a framework where I think one begins to answer this. And I know, for instance, Clark Barwick has an approach to equivariant spectra that sort of also gives an answer to that, and I'm pretty sure Jacob Lurie does somewhere in one of his books to be. So anyway, so I'm not, but I think it's useful, and as you're just stepping back and thinking about the subject and what aspects to engage with, this is already an interesting puzzle that how might I, in category theoretic terms, characterize what this arrow is doing. Well, this actually, there's something really interesting and fundamental going on here. So let me point this out. So now I did this kind of stabilization exactly so that I'd have Spanier-Whitehead duality. And as things work out, once I have Spanier-Whitehead duality, I get the following fact that finite G-sets are Spanier-Whitehead self-dual. Okay, so that means, in particular, that the map from a finite G set, so let's suppose this is a finite G set, into what I might call maps from S to X, or I could write this as that this map is always a weak equivalence. And if you just think about mapping a map into this is the same as a map from S smash the domain into X, and that's what I would get here if I used Spanier-Whitehead duality. Now I want to write this in a more compelling way. So this I want to write as a wedge over the elements of S of a single copy of X, and this I want to write as a product over the elements in S of a single copy of X. And now that resembles this notion of additivity, that a map from a finite sum to a finite product is an equivalence. And what the self-duality, so stabilizing with respect to representation spheres is not something we can kind of think of in terms of pure algebra, But this at least resembles an algebraic statement. It's saying that the map from a wedge to the product is an equivalence, but now I'm allowing the group to act on the indexing set of the wedge. So I like to think of this statement as an equivariant analog of additivity. Okay, so one consequence of stabilizing with respect to representation spheres is that we get equivariant additivity. But in fact, the two are equivalent. Because once I've dualized finite GCW complexes, then I have duals of once I've dualized finite G sets and I have ordinary duals, then I've dualized G mod H cross a disk, and therefore I've dualized every finite GCW complex, and representation spheres are finite GCW complexes. And for a technical reason, once those have duals, they're invertible. So don't worry if you don't understand that. The takeaway point is that this condition, which involves the topology of representation spheres, is very non-algebraic, and it sort of has something to do with how representation spheres are built as GCW complexes. That has a more algebraic sounding name, which is we're asking for an equivariant analog of additivity in which the group is allowed to act on the indexing set. So this is one of the things and I'm going to get to other examples of this. As we were writing this paper and we were investigating a multiplicative analog of this, we really found that when one wants to do an equivariant homotopy theories, anytime you have any kind of monoidal structure like the sum or the categorical product or the smash product, that in equivariant topology you really need to think of it, you need to allow the group to act on the indexing set, and that the sort of true equivariant notion involves what we call the indexed monoidal products. So I'll come back at the end and sort of try to articulate this a little more abstractly, but again, the takeaway point is that we could stabilize like this, and that guarantees Spanier-Whitehead duality, and it gives you the foundations for Poincaré duality and all that. But what we're doing in the finite group case is something algebraic, and that we're asking that an equivariant notion of additivity hold.
So is that like you had some sort of symmetric monoidal coproduct before, but now it's some sort of G-monoidal coproduct?
You can think of it as a G-monoidal coproduct, but I'll make a more careful statement at the end. I'm kind of hiding some things in this statement that I'll say more at the end. Shoot. Okay. Now, here's an amazing thing. It's a little bit of a puzzle. It's kind of an amazing fact. So now that we've got this category, we can ask, what can we say about what happens to some of our favorite things? Like, what's pi n of Sn or pi 0 of S0? In ordinary topology, that's the theory of the degree of the map, and it's an integer. But what would this be? So the first thing is, it's probably a little bit bigger than we expect, right? So that's the limit as v goes to infinity of maps from SV to SV up to homotopy. Oh, and these are equivariant maps. Now, if I have a subgroup of G, I can, since this map is equivariant, I can restrict to the fixed points for H. So I could send that to ordinary maps from the H fixed points to the H fixed points. And now these are just ordinary spheres. Their dimensions going to infinity. That's the ordinary pi n of Sn. And so this group is the integers. So one thing I get out of this set is an invariant. For every subgroup, I get a map from this group into the big product over all the subgroups of G of a copy of the integers. So I have a degree, I have a notion of degree for every subgroup. There's a little bit of redundancy in this information. The degree of a conjugate the map attached to a conjugate subgroup will be the same. So I could have made a more compact state. So this is clearly not an isomorphism because I've put some redundancy in here. But it's just to show you the theory of the degree of a map is going to be a little bit different in the equivariant homotopy. Now, I don't want to run out of time, and I really do want to illustrate a proof of something. So I'm not going to linger on that point, but I'm leading up to a beautiful theorem of Tom-Dijk. So I want to describe a beautiful theorem of Tom-Dijk, and I want to set it up in a way that you meet really what I think of as sort of really one of the maneuvers at the heart of equivariant homotopy theory. So Tom-Dijk asked more generally, what are maps from one finite G set to another in this category? And he introduced an algebraic approximation to that, which I'll call the Burnside category, Burn G. So the objects are finite G sets, and a map from S to T is another finite G set, U. A map is represented by a correspondence. So this is just a map of finite G sets. And in fact, I really want to take so these form a commutative, the isomorphism classes of correspondences form a commutative monoid under disjoint union, and I want to take the group completion. So the classic, the first thing to think about is to notice that if S is a point, so that's what's called the Burnside ring of G, which is the Grothendieck group of finite G sets. It's the Grothendieck group completion of the group of finite G sets. And because of equivariant additivity, because the finite G sets are self-dual, because of what's written on that board, if I have a correspondence like this, and I look at these as objects in the stable category, I could have the dual of this map and this map. So every time I have a correspondence, I actually get a map from S to T. And in fact, there's a functor from the Burnside category to the homotopy category of spectra that sends S to, well, spectra have a base point, so I'll just say S with a disjoint base point. And the fantastic theorem, which I think is due to Tom-Dijk, but maybe someone can correct me if I'm wrong, is that this map, this is fully faithful. Namely, that the map from Burn G S T to this is an isomorphism. All right. Yeah, I mean, Siegel gave a proof of this in his ICM talk. So,
I grew up learning that this was called a Siegel-Tom-Dijk.
Okay, all right. So, so in our latest episode of Clash of the Titans, I was defeated, and the younger Titans won, and so this is Siegel-Tom-Dijk. Okay, so Siegel and Tom-Dijk. This is so. There's also an infinity version of this that's also due to Siegel and Tom-Dijk that describes the entire spectrum of maps here in terms of non-equivariant homotopy theory. So I actually wanted to give you a proof of this It's surprisingly easy to prove, but it is the maneuver where but I think I wanted to give you the proof because I wanted to set up some things I'm going to tell you about a little bit later. But maybe before I do that, let me just ruminate on one key point here. Let me sketch the proof. I'm going to sketch the proof. So sketch proof. This is surprisingly easy to prove once you get yourself set up right. So by Spanier-Whitehead duality and reducing to orbits and things, it suffices to check it, and it suffices to do the case S equals T equals a point. And now, so now what I'm trying to prove is that the map from the Burnside ring to the maps between spheres is an isomorphism. I'm trying to prove that that's an isomorphism. And the first thing I can do is compose it with this map. And what this map does, what this composed map does, is it sends a finite G set, which I might as well call T, to the thing whose H component is just the number of H fixed points of T. And it's pretty easy to check that this map is a monomorphism. So it's easy to check that it's a monomorphism, and what you have to do is prove that it's an epimorphism. So for that, let's pick... So for that, I want to let T be a finite G set with the property that the G fixed points of T is empty, but the H fixed points for every proper subgroup of H is not empty. So I could take the disjoint union of G mod proper subgroups. So I'm just going to pick this G set. And I'm going to look at the mapping, the cofibration sequence T with the disjoint base point to S0 to what I'll just call T tilde. So that is, if this is T, T tilde is just the unreduced suspension of T. And so T tilde has the property that the G fixed points is just S0, and the H fixed points for H, a proper subgroup, is a bouquet of circles. Right, and now, so now we have this sequence. And down here, we have the maps in the Burnside category from a point to T, going to maps in the Burnside category from a point to itself, which is this. And we know by induction, this is described in terms of, this all has proper subgroups as orbits. So this is an isomorphism by induction on the order of the group. So we want to prove this map is surjective, and so by the Hesselholt epimorphism theorem, it suffices to show that this composed map is an epimorphism. I don't know. Okay. All right, now, this is the place, this is the moment in equivariant homotopy theory where everybody I used to listen to always started spelling stuff. So it turns out sort of rather miraculously that you can analyze this. And it's a sneaky little argument, and it takes some time to process it. So So it takes a little time to process it. And what is it I have to analyze? So this thing, so that's the limit as v goes to infinity of maps from SV into T tilde smash SV. Equivariant maps. So let's first look inside. Let's first look at what happens when I map the fixed points in. Okay, so this is a GCW complex, this SV, and as I remarked right at the beginning, it has a cell structure where I first build the fixed points, and then I add the non-fixed cells. So that, if I restrict to that, any map from here into here has to factor through the fixed points. And the fixed points of this is this same thing, and then the fixed points of that T tilde is the zero sphere. So on fixed points, I just have a map from here to here, and I get a copy of the integers. So what I'm imagining that I'm going to understand these maps by obstruction theory, and I started with the fixed points, and now I want to know what happens when I attach another cell. So when I attach another cell, so then I'm going to attach a cell of the form G mod H cross Sn. And this n, this number n, is smaller than the dimension of the fixed points, the parts of V that's invariant under H. After all, that sphere is fixed under H, and so that has to constitute part of the H fixed points of this representation sphere. So if I'm studying a map from here into this, then that's the same. That's the same as a map from this sphere in, or this might be a disk or whatever. It's a map from this sphere into the H fixed points of this. And that is a wedge of circles, smash SVH. And now you can see there's this tricky little thing that happened. This bumped the connectivity of this space up. So this map, this n was smaller than that. This is bumped up by 1, so this map is automatically null. All right, I'm going to let you kind of drive that home, but what that argument implies is that this is just the integers, and that this map sends a G set S to the number of invariant vectors, invariant points. I erased it. So that's the proof that this is surjective, and then, therefore, that's an isomorphism. Well, gosh, now I really only have, assuming there's no questions, I have 2 minutes left, and I have several points I want to make, so I'll make them a little bit rapidly. There's something very deep about this, and it tells you that, right, on one hand, we had this notion of equivariant additivity, and that had to do with finite G sets. And equivariant additivity. On the other hand, we had something about representation spheres and inverting representation spheres. And one thing Tom Dieck's theorem tells you that I find really surprising is that a big colimit of a system that involved only maps between representations spheres eventually output only information about finite G sets. There's something deep inside the Siegel-Tom Dieck theorem that reverses this direction and goes back from the representation spheres to the finite spheres. So that's something a little surprising. And in fact, there's a tremendous power in equivariant homotopy theory about playing off the cell structure of representation spheres and kind of this notion of finite additivity. So I was going to spend some time kind of really enumerating these things. What Mike and Doug and I introduced was a a variation of the Posnikov tower we called the slice tower, which exploits exactly that duality, or that kind of correspondence, and it led to some really surprising computations in equivariant homotopy theory. I had several other points to make, but let me I'm just going to end with just one single one. If this tells you that, so if the homotopy groups of sphere, the homotopy groups of any object in equivariant stable homotopy theory, so if X is one of these stable objects, then the homotopy groups of X, I really shouldn't just take maps of a sphere into X. I should really consider this aggregate of information, the equivariant maps from a finite G set into X. And this gives me an additive contravariant functor from the Burnside category into abelian groups that sends S to this. And such a functor, an additive functor on the Burnside category, is called a Mackey functor. And another thing you have to get used to when you're working with equivariant homotopy theory is that what used to be an abelian group is now a Mackey functor. And Mackey functors, they take some getting used to, but you can eventually learn to really think of them as you do abelian groups. Now, so they play exactly the same role as abelian groups do in ordinary algebraic topology. You can make an Eilenberg-MacLane space for any Mackey functor. You could ask about the equivariant Moore space problem for a Mackey functor, but honestly, until I just said that, I'd never asked about it or thought about it, so I don't know. But let me just tell you a problem. So because there's Eilenberg-MacLane spaces, there's cohomology with coefficients in a Mackey functor, and an interesting problem is to collide these 2 points of view and say what can you say? Describe the cohomology of these representation spheres with coefficients in M, where M is a Mackey functor. Our work on the covariant problem was predicated on the fact that we could do this in some very simple cases. But the general problem, it's one of these things that you can, if you work hard enough in any given example, you can do the calculation, but kind of really understanding the result at the end is a bit tricky. But there seems to be a lot of mileage in it, and one reason there's mileage in it is it's exactly forcing you to connect these 2 points of view, the sort of point of view of finite G sets and representation spheres. I've gone over time, so if there's more you want to know, ask me another day. Thank you.